Okay, guys, so today our topic is full adder, and in the previous lecture series, we have discussed about the half adder and the half adder implementation using the NAND and NOR gate. Okay, so the NAND and NOR gate are the universal logic gates, and how to implement the half adder circuit using the NAND and NOR gate that we have already discussed. So, in the current lecture, we are going to discuss about the full adder. Okay, so let us start. So this is the block diagram of the full adder. As you can see, with compared to the half adder, the full adder requires three input. In addition to the A and B, there is one more input to this full adder, that is we call as a carry in. So this carry in is the input from the previous addition. Okay, so if we are going to if we are going to add for the first time, then the input for this carry in will be 0, and whatever the value of A and B will be added, and then after the sum and the carry out will be generated. Now this carry out will act as an input to the next addition. Okay, so therefore we have three inputs, A, B as well as the carry in. Similar to the half adder, the full adder circuit also has two outputs. Among them, one is the sum and another is a carry out. In order to distinguish between the input and output, we have used the word carry in and the carry out. So this is the block diagram of the full adder. Now let us take an example to understand how the full adder is working and how it is different than the half adder. So let us assume that the input A is having a number 7 in the decimal form, and the input B is having a number 5 that is also in the decimal. Now as we all know that in the decimal system, the addition of 7 and 5 will generate the 12, and in this case the sum will be having a value 2 and the carry will be having a value 1. Now, since this is the full adder, apart from the input A and B, we have the third input, that is the carry in. Now let us assume that the value of the carry in is having a value 1 in the decimal. Therefore, we are not going to add only 7 and 5, but also will add the carry with the values of A and B. Therefore, it will be a 7 plus 5 plus 1. In the decimal, the value will become 13, and therefore the sum will be having a value 3 and the carry out will be having a value 1. I have assumed the decimal number system in order to make the explanation simple. However, the full adder circuit is designed to work with the binary number system. The same will be applicable to the binary number system, but for the simplification, the example was taken in the decimal number system. After understanding the block diagram, now let us move towards the truth table of the full adder. Similar to the half adder, full adder is also having a truth table. However, this time the input will be having three variables. That means the A and B are the variables which holds the actual value, and the third variable C in act as a carry input. Therefore, in actual, we have three variables A, B, and C. Since the full adder circuits are designed for the binary number system, the variables are also the binary, and therefore, with the three variables, we have 2 to the power 3, that means 8 possible combinations. The combinations are from 000 to 111. So these are the combination in which you can see starting from 000 to 111. Now apart from the input, in the truth table let us see what are the outputs. Similar to the half adder, full adder also has one of the inputs as a sum and another input as a carry. Now the truth table is prepared manually. So therefore let us start with the 000, and when we add those values 0 with 0 with 0, we get this sum as 0 and the carry also as a 0. Similarly for the next sequence, that is 001, the sum will be 1 and the carry will be 0. The same is applicable with the sequence 010. When we add these three bits, we get the sum as a 1 and the carry as a 0. For the sequence 011, now when we add 0 with 1, we get the value 1, and that 1 with the third variable which is also having a value 1, so 1 plus 1 is again 1 0. So in the 1 0, 0 will be the sum and the 1 will be the carry. Similarly, when we add this last sequence, that is 111, okay, so 1 plus 1 is 1 0, 1 0 plus 1 is 1 1, so that means 1 will be the sum and the carry will be the 1. So you need to keep this in mind that the truth table will be prepared manually by the person, and the truth table is used to verify your circuit. Okay, so this is the way you can prepare the truth table for the full adder. Now the next stage is to design the logic gates, or to identify which are the logic gates will be required in order to implement the sum. In this case, we are going to design or identify the requirement of the logic gates using the K-map. So our focus of our interest will be in the column of the sum. Now, how you can prepare the truth table, I mean the K-map, is that first of all you will see the number of combinations in the truth table. So there are 8 possible combinations for the input. Therefore, we will be having a K-map of size 2 cross 4. That means we have the 8 cells in the truth table. Now the organization of the variables in the K-map will be, on the one side we have the single variable A, and on the other side we have two variables B, C. Now each variable will take the normal form as well as the complemented form. So for the variable A, it will be, first of all we will have the complemented form and then the normal form. Similarly for the variable B, C, all possible combinations will be explored. That means first of all both the variables in a complemented form, then one variable in a complemented form and another is a normal, then both the variables in a normal form, and then again the first variable in a normal form and the second variable in a complemented form. So this way of arrangement will ultimately gives the cell as this value. That means the first cell is having value 0 0 0, which is indicated by A bar, B bar, C bar. Similarly, the second cell is having a value 001, which is explained as a bar, B bar and CE. Similarly, if you focus on the last cell, that is 110, can be explained as A, B, C bar. Now, when you will prepare a K-map and when you want to identify the expression for the particular output, in this case the sum, what you need to do, that you need to identify all the 1 in the column. So all the ones are circled over here, and now with respect to this corresponding row you have to, you need to verify the, you need to see the input sequence. So here for the 001, the output sum is 1. Therefore you need to see whenever in the 001 you will write 1. Again you will go back to the truth table, you will look for the 1 in the output, and for that you will see the status of the input. So here for the 010 also the sum is having a value 1. So you will see for the 010, okay, over here 010, so you will again put a value 1. Similarly, for the 100 we have the sum as output 1, and for the 111 we have the sum as output 1. So that means over here the value is 1, over here the value is 1. So this is the way you will prepare a K-map. Now once the K-map values are filled, it is very simple to identify the expression. So for this one, over here the cell value is 1, so that means you will write A bar, B bar, C in as the first expression plus this one. Okay, so that means A bar, B, C bar in. This for this one, the value will be A, B bar, C bar, and for the last one, the value will be A, B, C in. And when you will simplify this expression, the sum will be having the expression in this way, that is A XOR B XOR C. Therefore, the sum can be implemented by using two XOR gate. First time the XOR operation will be performed between A and B, and whatever the output will come, that will be XOR with C in. Now let us start designing the circuit for this sum. So as we have already identified that we require two XOR gate, one is over here which will be having a value as the input A and B, and therefore the XOR operation will be output as A XOR B, that will act as one of the input to the second XOR gate, and the second input to the second XOR gate will be simply the third variable C. Therefore the output of this XOR is one of the input A XOR B will be XOR with the second input C. So this way you can implement the sum in the full adder by using the 2 XOR gate. Now let us try to understand how we can design or implement the carry. So now instead of focusing on the sum column, we will focus on the column of the carry, and whenever we identify 1 at that position, we will in that input position we will put the value 1. So therefore over here we have the value 1 in the carry. We will look for the input A, B and C. So inputs are 0, 1, 1. Therefore for the 0, 1, 1 we will put the value 1. Similarly we put the value 1 at the 1, 0, 1, 1, 1, 0 and 1, 1, 1. Now the K map, we need to identify first of all the largest group. So in this 2 by 4 K map, the largest possible group can be of size 8, octet. However, we don't have the octet in this case. So next we try to identify for the chord. However, we cannot identify chord in this case. So the next one is a pair. So here our target is to identify the pair with the consecutive one together. Okay, so here we have three pairs. The first pair is for the cell number 101 and 111. This pair. The another pair is for the cell number 111 and 110, and the third pair will be with the cell 011 and 111. So these three cells together will be having a three expression. So let us try to understand how we get the AB. Okay, so let us focus on the cell number 101 and 111, that pair. So between that pair the common variable is A, as well as from this the common variable is C in. Therefore that pair will be having an output as a AC, which will be a third term in the expression. Now let us take the pair which is formed by the cell number 111 and 110. In that pair also the common term is A, and from the columns we have the common term as a B. So that means the A and B, the first term is formulated by the second pair. And now the third pair which was formulated by the cell number 011 and 111, the common term is B, C in. So this middle term in the expression is formulated by the third pair. So this way we can calculate or implement the expression for the carry. Now once the expression is formulated, the circuit design will be straightforward. You are going to add, or you are going to have three AND gate One AND gate is for the AB, another AND gate is for BC in, and the third AND gate is for the AC in. So therefore we have the like the first AND gate. I'm sorry, there is some mistake. Okay, there is no mistake, but the way of representation is something different. So instead of using the 3 AND gate, this expression is using A and B. We applied the AND gate, so there is a AB which was given as an input to the OR gate, and over here we have the another which is a expression BC plus AC. BC plus AC, no, BC plus AC. Let us go back to previous. Okay, so over here the input is C and the another input is A XOR B. So which will give us some output which will be given as an input to the OR gate, and finally with the help of that we will generate the AB plus BC plus AC. So this is the way you can design a carry for the full adder. So thank you very much for having your time. In the next lecture we will discuss about the half subtractor. Thank you.